Hello, and welcome to Astronomy 100. In the previous video segment, we had paid a visit to Palomar Observatory to see one of the largest telescopes in the world. And a couple of the ideas that we described at the observatory, I want to be able to elaborate with you here in this video. So let's go ahead and get started. So in that previous video, we had talked about why do astronomers use telescopes? And it was mentioned that the primary reason, the most important reason to use a telescope is to have the ability to gather light. The idea is fairly simple. The light that comes from an object is the information about that object. And so when we gather the light from that object, we are gathering information. And the objects that we're looking at are actually very, very far away. And in many cases, they're faint to the point where we just can't see them with our own eyes. So to have a telescope that has a very big opening to it, in other words, a big bucket, then what happens is that telescope allows you to gather more light. And when you gather more light, it makes an object that normally appears very faint appear brighter. The more photons of light that you gather, the brighter the object's going to look. Most people don't realize that the entire sky is covered with objects, many galaxies in every direction that you would normally look, but these galaxies are so faint that you just can't see them without a telescope. The human eye is not very good at gathering light. So objects that are normally too distant and too faint to be seen with normally the human eye are just impossible to see, can be seen with a telescope. Let me show you an example. So let's take the human eye, and we'll have an eye that's fully dilated, the pupil's fully dilated, and we're going to calculate how much light can the human eye gather. So the area of your pupil is simply pi r squared, and the typical radius of a human eye of your pupil is 0.15 centimeters. So we're going to square that, multiply it by pi, and what we end up getting is 0.07 square centimeters. So what that is that's the amount of area that your opening to your eye is capable of allowing light to come in. Think of it as your eye as a telescope only has an opening to it that's 0.07 square centimeters. However, if we were to use something like the Palomar Observatory 200-inch telescope that we visited in the previous segment, then now what we have is we have an opening that is 200 inches across. Think of it as this is your eye and your pupil is 200 inches across. So let's do a calculation with that. Now, the same formula, pi r squared, but when we convert it into metric units, 200 inches, and then, of course, taking the radius, which is 100 inches into centimeters, is 254 centimeters. So the radius of this telescope in metric units is 254 centimeters, square it times pi. And so what we get is 203,000 square centimeters of light gathering ability. So let's look at the ratio. If you compare what the 200-inch telescope at Palomar is capable of gathering to the human eye, you can see that a telescope such as this one can gather almost 3 million times the amount of light than your eye can see. So therefore an object will look 3 million times brighter when it's really too faint for you to see with the naked eye. So clearly a bigger bucket to gather more light is going to give you the ability to see very faint objects. Now, we mean this when we say a bigger bucket or a bigger telescope opening is better. So bigger is better. And what we know is, historically, there has been this drive to constantly build bigger and bigger telescopes within the limits of technology. Here is the original telescopes built by Galileo in 1609. And then for many years, the technology wasn't there to build them much bigger. In 1917, this was the largest telescope in the world. This is the 100-inch telescope at Mount Wilson Observatory near Los Angeles. And from 1917 to 1948, this was the largest telescope in the world. Well, George Ellery Hale, who built this telescope, then wanted one bigger, wanted one twice the size. So in 1948, the 200-inch telescope became fully operational, and that was the biggest telescope in the world for many, many years. In 1992, at Mauna Kea, the extinct volcano on the Big Island of Hawaii, there's the Keck Observatory, and there are now 2 identical telescopes that are about twice the size of the telescope at Palomar. So in 1992, this now became the largest telescope in the world, surpassing the 200-inch at Palomar. and on and on and on. So telescopes are continually being built bigger and bigger to gather more light, to see fainter objects, to look deeper in the universe. And currently, one of the biggest telescopes in the world that is being developed and designed at this point is called the 30-meter telescope. And this is an engineering drawing or artist illustration of what it will look like. And it will eventually be operational, maybe in the year 2022. But 30 meters, in other words, the distance of across the opening of this telescope will be 30 meters across. So we're talking almost 100 feet all the way across, as opposed to 17 feet for Palomar Observatory. So bigger and bigger and bigger is always the goal, to be able to see fainter objects. Now, the way that we gather light, once you have a bucket and you are gathering the light, you obviously need to bring that light to a focus. Traditionally, as with the early telescopes invented in the early 1600s, this was done with a lens. And the way that a lens works is called the principle of refraction. And the idea is that light that comes in from the distant object is going to bend as it goes through the glass. The shape of the glass and the principle of refraction work together to create a focal point, and this is where you would put your eye, so that you are gathering this much information and bringing it to this focal point right here. And so this is, again, the earliest and basic idea behind a telescope with lenses. The problem is that lenses are pieces of glass that are very thick, and when you try to build a very big lens to go with a very big telescope, the lenses become very, very heavy. The largest lens in the world, the largest lensed telescope, refracting telescope in the world, still currently sits in Williams Bay, Wisconsin. It's Yerkes Observatory, and here is a photograph of it from back in the 1930s. And you can actually see Albert Einstein as one of the people in this crowd. But the actual lens itself, shown in this photograph here, is 40 inches across. Now, 40 inches as opposed to a 200-inch telescope today, but that lens weighs hundreds and hundreds of pounds, very, very heavy, and it deforms under its own weight. So this is the biggest we were ever able to successfully build a lens without having gravity and the deformed shape of the mirror become a problem. The other thing you'll notice is that lenses require a long focal length, meaning that the lens sits up here, the light comes to a focus way down here, which makes for a very long telescope and, again, a very awkward setting. One final problem with telescopes that are built with lenses is that a lens suffers from a problem called chromatic aberration. The word chromatic comes from the word that means color. Chromo means color. So chromatic aberration means distortion of colors. And the way that this works is when the principle of refraction operates to bring light to a focus, what we know is the ability to bend light or refract light is what we call wavelength dependent. And what that means is it is different for different wavelengths. And so the light that contains all the colors of the rainbow comes in, but the different colors come to a focus at different points. So if you put your eye here, the object looks red. If you put your eye here, the object looks green. If you put your eye here, the object looks blue. So a normal object is going to have this color distortion. Notice the color distortions of this photograph of the planet Venus. You can see the red all the way through the blue. That's not normal. That's not natural. So chromatic aberration becomes a problem. The way that we solve this problem is we build telescopes with mirrors. And this was first really invented, if you will, by Isaac Newton. Isaac Newton realized that you can use what's called the principle of reflection to allow light to come in, reflect off of a mirror. As long as it's got a curved concave shape to it, the light will bounce, and every place the light bounces will be redirected to a point that is the focal point. So a mirror can do the same thing that a lens can do. The big advantage is, notice that the mirror can be very thin, and so you can build a very large mirror made out of glass and not have it weigh an enormous amount. The other thing is that mirrors do not suffer from chromatic aberration. The reflecting property of a mirror does not depend on wavelength, so you don't get that color distortion. Now you might notice that this poses a bit of a problem. Let me show you what I mean. This is the place where light comes to a focus. So this is where your eye needs to be. And if you think about it, the problem is the light comes in from this direction and your head or your eye is in the way. It has to basically pass you to bounce off of the mirror. That's just the way reflection works. So the normal curved shape of the mirror bounces the light to bring it to a focus at this point called the prime focus. But again, your eye has to be at that point to be able to see the object. So the solution to this is to take the mirror and to have a hole either drilled into the mirror or cast into the mirror and put a second convex mirror so that the light comes in, bounces off of the primary mirror, bounces off of the secondary mirror, and then gets redirected through the hole in the back. And so what you'll end up doing is put your eye outside of the telescope to be able to see everything that it saw. Of course, you're still getting some of the image blocked, you're getting some of the light blocked because of the small secondary mirror, but that can be minimized so that it's really not much of a problem. This is called a Cassegrain focus when you have your eye at the back of the telescope with a secondary mirror on the inside. All major astronomy-related observatories, astronomical telescopes of the world, use this concept. So it's a Cassegrain design that is used by all observatories of the world because the mirrors can be built very big, and you can also put your equipment on the bottom end of the telescope, and it's a very convenient place for that. So telescopes have grown quite a bit over the years, and today we prefer mirrors as opposed to lenses because of the properties of mirrors and the advantages of mirrors, and it is just the choice that astronomers use. Now, we're going to go back to Palomar Observatory to see how the telescope movement, or how a telescope is able to move and track the items of the sky. Let's see that. The 200-inch telescope is no longer the largest telescope in the world. In fact, there are a little more than 20 telescopes that are currently larger than this telescope. But the basic design of this telescope is still fairly the same throughout the world. Now, during the daytime, the telescope is stowed in this position. This is the home position where the workers during the day have easy access to the equipment that's at the bottom of the telescope. The mirror is down in this portion of the telescope right here. The opening of the telescope is up here. The light from your object that you're looking at comes in, reflects off of the primary mirror, and then comes to either a focus at the top, or you can redirect the light back down through the Cassegrain hole in the bottom. To be able to move the telescope, to be able to aim it at your object, or to be able to track the object that you're looking at throughout the night, the telescope needs to move in two different ways. The first direction that the telescope will move is in a north-south direction, in this case pointing all the way to the north celestial pole of the sky, and then has the ability to point from north all the way down to a certain position to the south. So this gets you the north-south movement of the telescope. And then the telescope has the ability to move from east to west, and that's what the horseshoe allows the telescope to do. So the mount is a very critical part of the telescope. It allows you to move the telescope around the sky and to line up on the object that you want to study. Throughout the night, though, once you have the object of interest in the view of the telescope will slowly track over the course of the night. So when the object has been found, very, very slowly, the telescope is going to move in essentially an east to west direction, very slowly. And this is what we call tracking. The idea is that you want the telescope to steadily move and track the object that you're studying, because the natural rotation of the Earth would normally make the object move out of the field of view of the telescope. So once the telescope is aimed at the object of your interest, then very slowly over the course of the night, the telescope will track, and forever long you want your observation to be, and then you can move the telescope on to the next target, and then of course you can track for that target as well. The telescope itself is 50 feet long. It has an opening of about 22 feet across. The horseshoe design has an edge-to-edge diameter of about 46 feet. The telescope, the mirror, and the mount all together weighs 530 tons, almost a little more than 1,000,000 pounds. And so the engineers back in the 1920s and 30s had to come up with a very, very creative way to be able to balance this telescope and allow it to move quite easily. Using ball bearings would have been impossible because the sheer weight of the telescope would have crushed the ball bearings. So instead, in this gap right in here, there are oil pressure pads that when you turn on a motor, it injects oil into these pressure pads, and it literally raises the telescope just a tiny fraction of an inch. And then it is so well balanced that when the clutches are turned off, just the fact that somebody could lean on the telescope will actually cause the telescope to move. That's how well balanced this telescope is. So for the 1920s and 30s, the engineering itself to make this telescope a reality was just absolutely marvelous, and it was one of the most creative ways to solve the problems of the day, and still to this day stands as quite an engineering marvel.